So, I've got a little story for you. Oh, I have to do this. Relax. I've got a little story for you. Let's see. Instead of reading the story, let me pull this over and let's have the same conversation just ourselves. So here's the conversation. Last time. And in your homework, you saw various things. You saw that if a sequence, we saw that if a sequence A converges, let's make sure that this is a sequence. A converges, then M. If a sequence converges, then two things. One, it's bounded. We proved it's eventually bounded, and then we proved that it's bounded. It's bounded. A is bounded, i.e., there exists some M positive. We added that to our little definition. We saw that that was useful to have, so that for all n, not eventually, for all n, a n is less than or equal to m. We saw that a sequence was bounded. We also saw that if a sequence converges, then for any subsequence, for all subsequences, these are maps from the naturals to the naturals, subsequences. Subsequence means, Joe? Strictly monotonic increasing, exactly. So for all I and j with I less than j, sigma I is strictly less than sigma j, right? For all subsequences, see, it's a subsequence of a sequence. So that means I'm fighting the fact that most people don't use subsequence for the map sigma. They use subsequence to mean A composed with sigma. But it's really a subsequence of a sequence. So this should be the subsequence, and this is the sequence. So this subsequence also converges, and to the same thing. Okay? I'm just reminding you, this is what we did last time, right? You remember these theorems have names. Let me not try to pull up what their names were. You can probably guess. This is like is bounded of converge, something like that. And this name is subseq limit. Anybody remember what it was called? I don't remember what it was called. It was called, we got a lot of theorems. Subseq conv. Subseq conv. The limit of A composed with sigma is the same as the originals. So subseq conv. Good. Go back and go back. This one was called subseq conv. I mean, it could also be called like 3.1. That's what books call theorems. I like to give them an actual name. So I don't know. Maybe it's easier to remember 3.1 than it is to remember subseq conv. Anyway, we have it there. All right. So we saw these two things, these two phenomena, and that's what Socrates says. And Simplicio says, yes, so what? Who cares? And Socrates said, then we also noticed that we had some other sequences, like here's another observation. The sequence an is equal to -1 to the n, plus or minus 1, does not converge. Does not converge. Of course, we proved that long ago, but is bounded. But is bounded. And last time we saw that it has a subsequence. It has a subsequence, namely the evens. Sigma of n is equal to 2n, which does converge. Okay. This is kind of a curious thing. So if a sequence converges, then it's bounded, and any subsequence also converges, and by the way, converges to the same thing as the original sequence. Also, here's a sequence that does not converge, but it is bounded, and it has some subsequence that converges. Simply shows like, what are you getting at? Well, if you're a mathematician, what's the kind of question you might ask in this situation? John.
They're all bounded sequences, not subsequences.
Beautiful, right? That's like, it's kind of, well, maybe I've set it up so that it's staring at you, but it is staring at you, right? So very natural question. Yeah. So natural question. Is it true that all bounded sequences have subsequences Jesus, so much easier to type, that converge? Okay, so just think about it. Think about it geometrically. Here's my sequence. It's bounded. So I'm between some minus, some m and minus m for some positive. So I'm doing whatever I'm doing. I'm not converging. I'm not saying I can't go backwards. That's a bad picture. Okay. But is there some subsequence of this thing? Some like choice of I'm going to take you, and then I'm going to take you, and then I'm going to take you, and then I'm going to take you. And you guys, when I pull them over to the left, right? That's what a subsequence is to take these various values and just line them up. Maybe that has a limit. And it seems pretty natural that that would happen because you have nowhere to go. You have infinitely many things that are all contained in a small region. There should be a limit. There should be some subsequence that has a limit, even if the sequence itself doesn't. Okay. You mean whether that always happens? Yeah, something like that. Can you elaborate? Okay. Maybe you're trying to tell me that if a sequence is bounded, then it converges. No, of course that can't be right, because -1 to the n is bounded, but it doesn't itself converge. Maybe you're saying that there's always some subsequence that converges, but that can't be right either, because the sequence a of n equals n, which just walks off to infinity, that doesn't have any subsequence that converges. But that sequence isn't bounded. So maybe what you're saying is, if a sequence is bounded, then there's always some subsequence that converges. Great. That is called the Bolzano-Weierstrass theorem. It's a very, very important theorem in this subject. And here's the problem with this theorem. It's not true for the rational numbers. So yes, this is called Bolzano-Weierstrass, very important theorem that we're going to get to very soon. Weierstrass. So Bolzano proved this in 1817. Weierstrass proved this in the 1860s. By the time Weierstrass proved it, people were ready to accept this as the mathematical framework that he was putting together that actually already existed in some form in 1817. But I'll explain to you why Bolzano couldn't have proved it in 1817, even though he did, even though he had all the ingredients. He was missing one ingredient, Damien. He did not use sorry in his lean proof. That is an outstanding, well, he kind of used sorry in his lean proof. He used sorry in the sense that he didn't know what the real numbers were. We can't prove this theorem honestly until we know what the real numbers are. And so let me say, the Bolzano-Weierstrass theorem is not true for the rationals. You can take sequences in the rational. So here's a sequence. I'm giving a sequence. AN goes like this. It goes 1. That's a rational number. 1 over 1. Rationals are fractions. Then it goes 14 over 10. Then it goes 141 over 100. Then it goes, what did I say here? What's root 2? 1.4142. 1.1414 over 1,000. And 1.4142 over 10,000. Okay, too many zeros. And so on. I'm getting this sequence is 1, and then 1.4, and then 1.41, and then 1.414, and then 1.4142, and so on. That's a sequence of rational numbers. It's fractions. It's certainly bounded. It's an increasing sequence. This sequence, this is an increasing sequence, increasing and bounded sequence. So none of these are going to get up to 2, for example, bounded sequence in the rational numbers, which doesn't converge in the rationals, which does not have a limit in Q. The limit, what I'm cooking up is just the decimal expansion of root 2. The limit is root 2, which is not in Q. By the way, do we ever prove that root 2 is irrational? Maybe I should add that. We did. You guys have, we haven't in this class. You guys have all seen the proof, all right? Maybe at some point we'll come back to it just for completeness. Okay, so in order to continue our conversation of real analysis, we have to stop and say, what the hell are real numbers? And I promised you this moment would come. Here it is. What are the real numbers? Okay, fine, I'm ready. Tell me what they are. Socrates. It's complicated. The reason I'm postponing this is because it's actually complicated. And I want to prepare us for the definition for it to land at the right time and place. So it's going to take us time to find the answer. But what do we want the real numbers to be? Other than John. Does anyone have a desire for the real numbers? What problems are real numbers supposed to be solving? Joe. Yep, between any two rationals, there's a real. We want them to be dense. We want them to solve this problem. We want, if there is a limit, then there should be a limit in the reals. Right? We want, if you give me decimal expansions, then that decimal expansion should converge to a real number. It does not converge to a rational number necessarily. Decimal expansions do not converge to rational numbers typically. But every decimal expansion should converge to a real number. Okay, so the idea is, this is what Simplicio says, we should have limits of rational sequences, so idea, the real numbers should be, I don't know what this means, limits of rationals. Limits of rational sequences if they converge. Okay, but wait a second, good. So you want to define a real number as limit of a sequence of rationals that converges. What does it mean for a sequence to have a limit? For all epsilon, there exists an n, yada yada. You get over, you get closer and closer to some real number L. To some L. Okay, and what kind of number is this hypothetical limit L? It's a real number. Uh-oh. We're trying to define real numbers as sequences of rationals that converge to a limit, and that limit is a real number. And that's how you realize we're going around in circles. The way to define real numbers is in terms of limits, but the way to state what a limit is in terms of real numbers. And this is begging the question. We're going around in circles. This is circular logic. So the very notion of limit that we've been using presupposes the existence of real numbers. And somehow we have to break this. So Simplicio says, so we're stuck. There is no way to define the real numbers. We're screwed. Right? What are we going to do? And Simplicio says, this is where Cauchy, the reason Cauchy's name is so highly revered in this subject, among many other reasons, is that he had a brilliant insight. You can't use the real numbers to define limits. You want to say AN gets closer and closer to L, but you don't have L. You have to say AN gets closer and closer to something else, not L, because you don't have L. What should it get closer and closer to? I love this moment. Once you see it, you can't unsee it. And until you see it, it's very difficult to see. Sean. Yes, exactly right. Okay, so Simplicio says he has nothing else to play with. Exactly. So the sequence has to get closer and closer to itself. That's the big idea. That's the breakthrough that Cauchy had. That instead of talking about getting closer and closer to L, we're going to talk about getting closer and closer to itself. But what does that mean? Okay, so how exactly are you going to do that? So let me make a little bit of room here. Limits of Q, limits use R in the definition. So that's no good. No good. We'll be going around in circles. Yes, that's the sound I'm going for. Exactly right. Exactly right. So Cauchy's brilliant insight is that you can solve this problem instead of AN getting closer and closer to L. Get AN, you have nothing else. Get AN closer and closer to itself. Now, of course, you can't say AN minus AN is less than epsilon. That makes no sense, right? AN minus AN is less than epsilon is a useless thing. So you just have to give yourself two different indices. AN and AM have to get within epsilon once N and M are both large. Once N and M are both large. Both large. Okay? So if A and M are both within epsilon of each other, that maybe could be a substitute for convergence. That's very clever. So instead of saying we converge to L, we just say we converge, we get closer and closer to ourselves, and that will be a substitute for that. Can you write that in terms of epsilons and deltas? So let's make a formal definition. So simpliciter says we'll say a sequence has a limit if there exists an n, so that for all m and n greater than n, an minus am is less than epsilon. The problem is we already have a notion of has a limit, so we're going to give that a different name. And the name we give that is Cauchy. So here's our main definition. Definition, a sequence A, which is a map from the naturals to the reals, well, to anything, by the way, not just to the reals, but to any field, to any type. I don't even have to X. Of course, we're going to think of X as rationals or X as the reals. But a sequence is just, a list of things, whatever those things are. A sequence is Cauchy if for all epsilon positive, there exists an n, natural number n, so that for all m at least n, and for all n at least n, the difference from am to an is at most epsilon. Okay? Does that make sense? Second.
Would it be possible to simplify this definition by just saying n equals n plus 1, something like that?
Excellent question. Okay, so there's going to be a homework about that. Could Cauchy have used n and n plus 1? Outstanding question. I'll put it here in the notes just to record it. Question: can we compare n and n plus 1 instead? And if we could have, we probably would have used it. So there's going to be a homework problem that shows you why that's not enough. Although I'm giving it away by telling you that. There's a homework problem that will ask you whether it's enough or not. Thank you. I mean, I'm a...
Is it the definition that says for all n greater than n, for all n greater than n? And if you use n and n plus 1 and n plus 1, can you value substitute for n because it is greater than n?
That's right. So among these, you will be able to test whether this inequality holds for n and the next value. But you'll also, I claim, need to be able to test it for more values. Okay. Right. So we say that a sequence is Cauchy if exactly this holds. And this definition is one of the most important definitions in all of mathematics. You're going to see this again when you study Banach spaces, functional analysis. You're going to see this again when you do p-adic analysis, p-adic numbers, and if you go into number theory and arithmetic. You're going to see this again when you do metric spaces and metric completion of metric spaces. Okay, it's a very universal idea that if you are trying to understand convergence, but you don't know what the limits are, you use the sequence against itself. If you have some way of measuring distance, then you just measure, if you have something like a norm. So this is really a Cauchy sequence is something that acts on a normed field, or not even a field. We just need to be able to, a normed ring or something. We just need to be able to add and subtract. We need to be able to say this. So it's like a normed group. All I'm asking for is that the ANs can be subtracted and that we have a norm on it. Okay, exactly.
So this definition in no way relies on the existence of real numbers.
Correct. Because we can take it, epsilon could be just rational numbers. Yeah, so let's make this definition. Let's make this for our purposes. Well, for our eventual purposes, eventually this is the version that we'll want. Eventual purposes, we have a norm on the rational numbers, right? The absolute value of -7 over 14. That's a poor choice. Over 15. We know what that is, right? We have an absolute value function on the rationals. So we know what it means for epsilon to be positive as a rational number. So a sequence of rationals, a map from N to Q is Cauchy if for all rational number epsilon, if epsilon is positive, then, let me make this look a little bit less weird, then there exists a natural number n. So far, we're only using natural numbers and rational numbers, so that for all m and n, at least n, the difference between a n, which is a rational number, minus a m, which is a rational number, is in absolute value, which is a rational function, is less than epsilon. Okay, so I'm never using the real numbers in this process. That's the miracle, is that we can do everything without ever referencing the real numbers. All right, so before we get back to what this has to do with the real numbers, now that we have a new definition, let's get a little bit of practice with this new definition. And then we'll come back, maybe even today, we'll try to come back and see what we can do with it. All right, make sense? So this new definition, let's play with it. Let's see where we can get. All right. So here's our first big boss. Please. Okay, so our first big boss is we have a sequence A, which already takes values in the real numbers. So again, I'm presupposing we have the real numbers. We're going to come back to how do we get rid of that presupposition. If we have the real numbers, I have a sequence from the natural to the reals. I have the fact that the sequence converges, and I want to prove that it is Cauchy. Okay, so let me state this. Let's work on paper. What's that?
Now we learn the absolute value subtraction thing.
Yes, exactly. This would have been useful, right? There's a bunch of ways that we're going to speed up our leanification of things that you'll see in just a second. I want to like make this. We're getting better and better at it, which means we need to be faster and faster at doing these kinds of things. So let's add this theorem. This theorem says that subtraction is commutative. So of course, subtraction is not commutative, but when you have absolute values, subtraction is commutative. So absolute value of xy, x minus y is absolute value of y minus x. All right, given that theorem, let's work out the proof of this goal. So here's our theorem. We're given a sequence. Again, we're going to pretend that we know what the real numbers are. So we'll given a sequence and the fact, I guess I called this fact HA, that A converges. So seq conv A, prove, or our goal is to show is Cauchy A. Okay. Let's work through this. So how does is Cauchy start? Should we change to the definition? Would that be a useful thing? No, you guys, how many want to see the definition one more time? Okay, enough of you want to see the definition. So we'll start with changing to the definition. Let's change the goal to say for all epsilon positive. Now we can take epsilon to be real. In fact, we need to take epsilon to be real because we're going to compare it to real numbers. For all epsilon positive, there exists an n, which is a natural number. For all m at least n, and for all n at least n, absolute value of am minus an is less than epsilon. Okay, so the order as human beings, of course, doesn't matter, but in lean, this is a function. So the function will first want natural number m, then it will want a proof that that natural number m is at least your other natural number, capital N. Then it will want another natural number n, then it will want a proof that that natural number n is greater than or equal to n. And then you can't switch this m and n either because they're referring to particular values of m and n. Okay, so we actually do want it in the order as given. As human beings, I don't care. Right.
I was gonna say, like, on a test, you swap.
As human beings, yeah, we understand that those things are the same. All right, so we've changed the goal to now say this. So what's our first step? Let's intro, yeah. So intro epsilon and h epsilon. So in natural language, let epsilon be given and assume that epsilon is positive. Okay, so now the goal says there exists an n. Where are we going to get that n? Sean? From the convergence of A. So we have to, how are we going to get the convergence of A? Remember, what does seq_conv mean? Joe? Exactly. So what do we want to do? Let's get that L. Exactly right. So let's choose L, HL using HA. Okay. So now we have something called HL. Slide this up. We have something called HL, which says, yes, seqlim, exactly right. Seqlim AL, which is the same thing under the hood. We could change it also, but I think we don't need to. HL under the hood says for all epsilon positive, there exists an n, so that for all n greater than n, an minus L, now we have an L, is less than epsilon. What are we going to do? How are we going to prove that AM gets closer and closer to AN Jeffrey?
Use epsilon number 2, and then you can use that triangle.
Exactly right. This should be a familiar trick. So the idea is, yeah, let's draw a picture. I neglected to draw a picture. We should always start by drawing a picture. So here's our little picture. We have a sequence. We know that the sequence converges to L, whatever it's doing. And now I want to compare some, once I'm past N, I'm within epsilon of L forever. And now I want to say, I have two points in this sequence. How far apart could they be? Well, if this window is epsilon, they could be 2 epsilon apart. So I want to shrink that window to be epsilon over 2. And now each one is within epsilon over 2 of L. So the idea, get AN and AM within epsilon over 2 of L. Okay, so so I want to specialize HL to what value of epsilon? Epsilon over 2. Why is it positive? By bound. And then this says there exists so HL, once I feed it the epsilon over 2 and the fact that epsilon over 2 is positive, says for all, it says there exists an n, so that yada yada. So I can immediately choose it. So in one line, we can do what we used to take 3 or 4 lines to do. Let's just choose an N and HN using this. You see what that's going to do? So HL is a function. It got a value of epsilon, namely epsilon over 2. It got a proof that that was positive. Now it says there exists an N, so that for all N, yada, yada. And so give me that N and HN. We're going to get very efficient with our lean. Okay, so now HN says the following. HN says for all N at least N, AN minus L is less than epsilon over 2. So let's record that. Sorry. So we've chosen that capital N, and the goal says at this point, Ayman? Yeah, we're still here. We're still here. The goal wants a capital N. Which value of capital N? The one that we have. Yeah, use capital N. Okay, what is the new goal? At this point, the goal says for all M at least N and for all N at least N, yada, yada. So now what do we want to do? Intro what? M, HM, N, HN. Give me the M, give me the fact that it's at least M. Give me the N, give me the fact that N is at least N. Okay, so now the goal says, so now we have a new goal. For that value of M and N, I want to show that AM minus AN is less than epsilon. What's that?
You need like 2 of the same thing.
I do. So I can create that with, yeah, let's do a have. Let's do a have, hypothesis on M, well, we already have a hypothesis, let's call it HM prime. HM prime is the fact that I want to get out of this, that AM minus L is less than epsilon over 2. That's going to be by apply. And how do I cook it up? I need HN. Which value of little n do I feed it? M. And who's my proof that M is at least N? HM. Everybody see that? Then let's do it again. Have HN prime, which says that AN minus L is less than epsilon over 2. That's by apply the same HN, but now with little n and HN. Okay, so we have these two inequalities. Our goal is this. What are we going to do? Joe sees, Akil sees, Sean sees, John sees, Roger. Say it again. You add, you're saying you add L and subtract L here? Oh.
The two statements.
Yes,
You just added up, you added them, right?
I agree. That'll tell us that these two, the sum of these two is at most epsilon, but how do I compare that to what I want? Triangle inequality on what? But this absolute value is, so the triangle inequality just here says absolute value of M, AM, plus absolute value of AN is an upper bound for this. Bingo. Bingo. So let's add and subtract L. Here's a really slick way to do it. It's not that slick. Let's rewrite the fact that AM minus AN is the same thing as AM minus L. I didn't give myself enough room. Plus L minus AN. And let's rewrite that fact into the goal. And what proves this fact? Ring. So you can say by ring normal form, by ring normal form, this is true, and rewrite by this fact. You see why I didn't teach you these things right away. Now you can start to build them up bit by bit. The goal will become AM minus L plus L minus AN is less than epsilon. Seven. So this is always a term of this type. The type is a proof that this thing is the statement that this equality holds. And among the set of all possible proofs of this, one of the possible proofs is by ring. This is a type, and this is a term. In exactly the same way as when you state a theorem, well, I don't have anything I can point to. If you think about it for a minute, you'll see that this, when you state a theorem, you say theorem, and then you give the hypotheses, and you say what you want to demonstrate, and then you actually have to demonstrate. So this is the what you want to demonstrate, and then why is it true? We want to give a term of type this fact, and the way to construct that term is just to prove it by ring.
You had set up our term called equals.
If we had these the other way around.
You used the colon equals operator.
Colon equals, yes. The colon equals operator is the creation of that term, but Lean can create that term automatically if it knows what kind of term it is.
Would it understand if I said right-hand side colon equals by ring them?
No.
All right, I'll
Yeah. Question, Ben? I'm introducing some new syntax to you. Okay, this works, as you'll see in a second. All right, so what this is going to do is it's going to find AM minus AL. It'll change that. Now now it's not about rewriting, because rewriting is about equalities. I want to chain inequalities, so let's go back to our usual thing. So we'll have fact one, which is that this absolute value blah blah plus blah blah is less than absolute value of AM minus L plus absolute value of L minus AN. And that's by apply abs-ad, triangle inequality. Okay, so I have this already being at most epsilon over 2. This is the wrong way around. Substitution commutes when it's in. So let's have F2 that L minus AN. And again, I didn't tell you this theorem because I was hoping not to tell you any names of theorems, but I had to tell you more and more names of theorems because the tactics weren't powerful enough. And at this point, we should just know this theorem. Apply abs sub com. Subtraction commutes under absolute value. Sure. Yeah. Great. Let's do it. So instead of what I said, let's do a rewrite by apply abs sub com of type this. And we're going to do that rewrite at F1. And that will flip L and L minus AN into AN minus L at F1. Okay. And now we're done. And now it's Linnerith. So which things do we have to put together to make this? So F1 breaks the triangle inequality. The first bit is HM prime. The second bit got turned around already. And so now it's just HN prime. And we should be done. Does that make sense? Let's try it. Okay. Is Cauchy. So from the top. Intro epsilon H epsilon as always. Intro, not as always, because it's a new situation. So I introed epsilon H epsilon. That gave us this goal. There exists an n, so that for all m and for all n, am minus an is less than epsilon. Okay? What do we do next? Let's get the fact that it converges. Let's get where it converges to. Choose LHL using HA. Okay. Now what? Yeah, in one fell swoop, we know that this says for all epsilon positive, there exists an n. I want that n, and I'm going to stick in epsilon over 2. So I'll say choose NHN using HL with epsilon replaced by epsilon over 2. And why is epsilon over 2 positive? By bound. Boom, we have our capital N. And we know that for all n greater than capital N, we have this inequality. Next, that's the n we want to use. Okay, and now we have a bunch of for alls. So let's intro M, HM, and HN. We've got our M and N, and we've got HM and HN. So far, so good? Okay, here comes a slick line. I'm going to do this rewrite. So by ring normal form, I want to replace AM minus AN by AM minus L in absolute value plus L minus AN. And I'm missing an abs close parenthesis. There we go. Did it do it twice or not? Okay, good. Sometimes there's a bug where it does it twice if there's a, right? It like doesn't erase the line. I should note that bug. Okay. There we are. So what did it do? That rewrite changed the goal from AM minus AN to AM minus L plus L minus AN. Okay, let's get the triangle inequality. Have F1 that this whole thing is bounded by this. That's by apply abs add. Okay, let's turn this L minus AN around. So let's do a rewrite. Rewrite by what? By apply abs sub com. What do we want to do? That the absolute value of L minus AN is equal to the absolute value of AN minus L. And where do I want to apply that? At F1. Does everybody see that? Boom. F1 got turned around. Cool. You want me to scroll up? You want to see anything? Make sense? Makes sense what happened and how it happened and why it happened? All right, now we're done. Combine F1. Yep, Damien. Oh yeah, we're not done. We're not done. Thank you. We're almost done. I got a little too trigger happy. Let's get our HM prime, which is that AM minus L is less than epsilon over 2. There is a way to do it too slick. One thing at a time. By apply what? HN with little n being m, the fact that little m is positive, is greater than capital N is that. And let me copy this. All right, so we're recording this inequality. Let's record the other inequality, HN prime, that AN minus L is also small. That's because of N and HN. And now we're done. Linarith, F1 matches the left-hand side. This is bounded by HM prime. The other one's bounded by HN prime and epsilon over 2 plus epsilon over 2. Brandon. Oh, that's I actually, that you can't tell, but that is an M. It's a very, very poorly written M. Yeah. Yeah. Akio.
HL from HA, got rid of HA from and from HL to the.
Yeah, it's because, very good question. So let me go to where that happened. Here. So if, when you choose with just one thing, it kills that one thing. When you take that one thing and you put lots of variables in it, you actually change it. And so it's temporarily creating some HL prime, then destroying that HL prime, but without touching the original HL. Okay, so if this was just choose using HL, yes, it would destroy it. But because we changed HL on the fly, it didn't know what to do with it, so it just left it there just to be safe. Very good question. Okay, makes sense? We're happy with the fact that so what have we proved? If a sequence converges, then it is Cauchy. How about the converse? If a sequence is Cauchy, does it converge? That's what we're going to get to. Probably not today. It's an extremely deep question. Okay, next exercise. Everybody ready? Next exercise. What are some of the other things we did with sequences and limits? We proved that sums of, if a sequence converges to L and another sequence converges to M, then the sum of A and B converges to L plus M. We do not know that A and B, either A or B has a limit at the moment. All we are assuming about them is that they are Cauchy. Let's get more practice with definition of what it means to be Cauchy. I'm still assuming that there's sequences into the real numbers, just for simplicity right now. Let's prove that the sum of A plus B is also a Cauchy sequence. Okay. Should I give you a minute to think about this? Is this a good quiz? Yeah. Let's do it. Yeah, go ahead. Akio.
A plus B of M is a bit of
Very good. So there is a summation operation on functions if the target has a summation, and it means exactly what you think it means. And if you aren't sure if Lean will see that A plus B of M is A of M plus B of M, you can always change. Right? Change. And in fact, we'll need that change. So let's take a good 5 minutes. I'll write the theorem here, and we'll make this our quiz. Yeah, sure. Do it in natural language. Yeah, do it in natural language and maybe think about how you would do it in formal language if you want to warm up to that. So the theorem is, if A and B are Cauchy, so is A plus B. A plus B, whose type is N to R. The idea or sketch out the idea, and if you can turn it into a proof, even better. We should be getting pretty good at this kind of stuff. You can talk to each other fake quiz. Friday, not Friday. A week from today, we'll have a real quiz. 15 minutes.
Bi-directional.
Add is one directional, it's, A plus B and absolute value is less than or equal to absolute value of A plus absolute value.
But then add.
No. But you can look up something and say,
Like mathematically, it's true.
is what true?
If absolute value of A plus B is less than, oh wait, never mind, I think I'm thinking about it. Not. But it's not an equality.
It's not an equality. You have the. What's the key idea?
Since you have A and B and you have B, this machine, you know that there's just an N1, so there's not less than two, bingo.
Yeah, so you get an N1 for epsilon over 2, you get an N2 for epsilon over 2. And should we do it together? Or do you guys, who wants more time? Everybody's okay to do it together? Let's do it together. Okay, so again, is Cauchy starts with for all epsilon, so let's intro epsilon H epsilon. Okay, that's going to tell us there exists an N is what we're trying to prove. Our goal is there exists an N. So let's grab N's from HA and HB. So let's choose N1 HN1 using HA with not epsilon, but epsilon over 2. And why is epsilon over 2 positive? By bound. And let's choose N2 HN2 using HB with epsilon over 2 and by bound. Okay, we have our N1 and N2. Sam, add them, yeah. This is our cheap replacement for the max. Use N1 plus N2. Now the goal says for all M at least N, for all N at least N. So intro what? M, HM, N, HN. Yeah, let's intro all of those things. Intro M, HM, N, HN. Okay, so the goal now says absolute value. Well, it's going to say A plus B of M minus A plus B of N is less than epsilon. And that doesn't look so nice. So let's change it. Let's change the goal so that it says AM plus BM minus AN plus BN is less than epsilon. Okay, so that's the thing that will get Lean to see that the sum of two functions evaluated at a value is by definition the sum of the two values. Now what? Now let's rearrange things. So let's rewrite by ring normal form, the fact that AM plus BM minus AN plus BN is the same thing as Savik. Exactly. Which is what we're going to see in N1 and N2, close parenthesis, close bracket. Okay, so now that's going to be in the goal. And let's have a F1 where we apply the triangle inequality. So AM minus AN plus BM minus BN is at most AM minus AN plus BM minus BN. And that's a less than or equal to by yada yada. You can fill that in. That's easy. Why is AM minus AN have whatever, I guess, HA prime or something, is that AM minus AN is less than epsilon over 2. That's by apply HN1, which we got over here. HN1 needs a value of M, which is M, a proof that M is at least N1 by bound. Then it needs a value of N, namely N, and then it needs another by bound. And then it'll prove exactly this. And then we have a HB prime, yada, yada, with B's instead of A's. And then we're done. Linearith F1, HA prime, HB prime. Did anybody get something like that, John?
I question about like how to translate into
Natural language.
Um,
Yeah.
So when the goal state is for all, you say let whatever.
Let F1 begin. Yeah.
Arbitrary or whatever. But then when the goal state is there exists, we usually say use.
Yeah.
How does that usually translate?
Use.
Just okay. Just say use.
Yeah.
All right.
Or you can say take N and take M and N larger than, greater than or equal to that capital N.
Okay, so you can go right to the for all, but just.
Yeah. Once you do formal proofs, natural language proofs are awkward in just how imprecise they are. Read one of your textbooks now and say, oh my God, you accept this as a proof? I wouldn't accept this as a proof now, even though it's crystal clear. In the same way that if you read paragraphs worth of mathematics that's supposed to represent algebra, you would similarly struggle with it. All right. Okay, so hand those over to Joe, or can I pick on Sean for today? Sean's our point man. And let's try it in, let's see if it works. So here we are. Let's do it. Intro epsilon, H epsilon. I have one more level I want to get to today. All right, so the intro gave us the Cauchy definition. Then I'll stick in the choose. So choose N1, HN1 using HA with epsilon replaced by epsilon over 2. Why is epsilon over 2 positive? Because of bound. Everybody see that? Now let's do the same thing again with N2, HN2, and HB. So far, so good. We've got our N1 and N2, so that if N and M are big enough, then we get these bounds. Let's use that for use N1 plus N2, and then intro M, HM, and HN. Now that doesn't look so nice, so let's change what it says there, bless you, to AM plus BM minus AN plus BN is less than epsilon. That's better. And now let's rewrite by ring normal form the fact that AM plus BM minus, oh, see, that's what happens. That's how I lost that parenthesis last time. AN minus plus BN. That thing is equal to, yeah, I think it's easier just to write it out. AM minus AN plus BM minus BN. I hope I got that right. We're going to find out in a second. Yes. Damon. Back.
Why is it different? How does the know
Yeah. The reason lean is letting you write this is that it knows if you have a function from a domain to a range, and on the range you have addition, then you have addition of functions. The definition of the addition of functions is f of 12, f plus g of 12. Well, you look at what f of 12 is, and you look at what g of 12 is, and you add that. So what it used to say up here, a plus b at m, by definition is the same thing as a at m plus b of m. It's just Lean's not gonna see through that definition unless we remind it that's what it's supposed to mean. If I tried to jump, if I didn't do this line and I tried to jump straight to the rewrite, I think it wouldn't work. Should we try it? I'm gonna copy this and I'm gonna retry this line. And instead of this change, I'm gonna go straight to the rewrite. Didn't work. Okay, so it's not, it should be smarter. This is one thing where it should be smarter. Go ahead, Dave.
If I initially like change, it's not to use the right definitions, they don't change things, but if I at the very beginning change.
Yes,
Then if I use the definition you just put up there, it'll be fine.
exactly right. Had you from the very beginning unfolded the definition of is Cauchy
I just,
with for all epsilon there exists an n, for all m, for all n, absolute value of parenthesis am plus bm, they would have taken it. Okay, so change is actually a little bit more powerful apparently than rewrite, because rewrite can't see through that little difference, but change can. So now I have to remember what the change was. Change absolute value of am plus bm minus an plus bn in absolute values less than epsilon. I haven't done anything mathematically. I've just adjusted things. I hope I still have this copied and pasted. Okay, we got our rewrite. All right, let's get the triangle inequality. Have f that this is less than or equal to the same thing, but with it. Oh, wait a second. What happened here? The change didn't work? We broke it. Let's just reload. It accepted the rewrite? It heard me badmouth it. Okay, we're gonna have to try this. Let's open this up for a second. Reload. Okay, what's the matter? Oh, yeah, that's what's the matter. That rewrite failed, and then everything else wasn't working. Okay, there we are. So, have f that this is less than or equal to that absolute value. That's by applying the triangle inequality, abs add. Okay. Should we do it the super slick way? The super slick way is to go straight to linearith with f. Now I want to use hn1, where for m, I give it m. Why is that true? It's true by bound. For n, I give it n. Why is that true? That's true by bound. And this is a proof of the fact that this is less than epsilon over 2. And Lean will synthesize all of that. And then also, let's give it the same thing with b, n by bound. And we got it all. Okay, so now we're getting really, these things are going to start moving. So much so that I think the next one we can do in 6 minutes. Actually, that clock's a little fast. We have 9 minutes according to my watch. We'll definitely be able to do it. Okay, so what do we learn? We don't know that Cauchy sequences, if a sequence is Cauchy, we don't yet know that it has a limit. We know that limits add. If you have a limit, if A has a limit L and B has a limit M, then the limits add. With Cauchy, we don't say what they add to, because the whole point of Cauchy is that we don't say what the limit is. But at least we know that if A is Cauchy and B is Cauchy, then their sum is also Cauchy. Let's get one more property. And let's see how quickly, let's see if we can do this one without going to the paper. Let's see if we can do it straight in the game. The goal is to prove that a sequence is bounded if it's Cauchy. We know that if it has a limit, then it's bounded. Let's see if it's Cauchy that it's bounded. All right, here's the idea. The idea is the sequence is Cauchy, so it's getting closer and closer to itself. But at some point, it will be within a window of width 1 of itself. And wherever that window starts, whatever the value of an is, in absolute value, will never go above an plus 1. Okay, so let's try specializing. Let's start the proof by specialize HA to epsilon equals 1 and y is 1 greater than 0 by bound. Okay, so there exists some A. And in fact, let's not specialize. Let's jump straight to choosing that n. choose NHN using that. That's an even better way to start. Okay, so we have an N, and we know that for all large enough values of M and N, this thing is less than 1. So I claim that the sequence will be bounded by A at capital N plus 1. So the bound that I want to use, seek bounded is there exists some bound, there exists some M. I want to use the absolute value of AN plus 1. That's for all of the tail. The tail will never get higher than AN plus 1. How about the initial terms? Let's add them up. Plus a sum of K in the range up to N of absolute value of AK. Is bounded has 2 components. It's that the thing is positive and that for all values, that's an upper bound. So before we split ands, let's make sure to record everything we're going to need. Let's record the fact that A of N in absolute value is positive. So have AN non-neg 0 less than or equal to absolute value of AN. That's by bound. Let's record the fact that this summation is non-negative. So let's have sum non-neg, which is that this whole summation, sum as K ranges up to N, AK is non-negative. Why is that true? Anybody remember? It's called sum non-neg. Sum non-neg. Now, sum non-neg needs a proof that all the terms are non-negative. And we used to do that separately, but now we just say by bound. Because bound was a proof that all the terms are other sums non-negative. Okay, so we know that AN is non-negative. We know that these things are non-negative. Let's also record the fact that AN is bounded by each of the terms. So if AN, let's call this have, I don't know, I'll just call it H. Have H for all N less than capital N, A of N is less than or equal to a sum over K in the range of absolute value of AK. And that's by applying, that was a theorem that we had, term LE sum. By apply term LE sum, and I think that will just do it. Good. Okay, so Lean figured out what sequence it should apply it to. It figured out what capital number N it should apply it to. And then we have all these inequalities. Okay, so we know that if N is less than N, then one of the terms is less than the sum of all those terms. We know that that whole sum is non-negative. We know that AN itself is non-negative. I think we're ready to split the ends. Split ends. We have an active goal and a sub-goal. The first goal is that the sum of these things is positive, while these things are non-negative, and it should know that one is strictly positive. So this is linearith. Linearith on what? AN is non-negative and that the sum is non-negative. And that's all we needed. That intermediate goal is gone. Next goal, for all N, we need to do this. Intro N. How are we going to prove this inequality? By cases. By cases, HN, whether N is less than capital N. All right. If it is less than capital N, then why is this true? It's true because of this. So let's jump straight to linearith, where we take H, we feed it N and HN. So H is for all little n. Which little n? This little n. The fact that little n is less than n is the hypothesis HN. So that'll give us this inequality. The AN is at most this sum. And then I also need to record the non-negativity of this. The non-negativity of this is AN and N. Boom. Next. Why is this true? Now it's not true that N is less than N, but for all large enough values. So now let's take this a little bit slow. Let me specialize this HN. So specialize HN. What value of N will I take? Capital N. Exactly. Capital N. Why is capital N greater than or equal to capital N? Bound will do that. What value of little n? Little n. And why is little n? I think if I give it HN, it's not going to be happy. But bound will figure out that this is implies this. That it's not true that n is strictly less than capital N implies that n is greater than or equal to. So let's try by bound again. Great. So now HN says that AN, whatever it is within one of A capital N. Okay, so let's think about this. How are we going to get an upper bound for AN? If we want an upper bound for AN, let's have F1, the fact that AN is equal to, what's the idea? Sean. Beautiful. Yeah, you guys are getting it. I'm going to subtract A capital N, and I'm going to add back A capital N. Let me make sure that I think the parentheses were unnecessary, but just in case, by ring, right? That's just ring. So that's the left-hand side is equal to this thing. This thing is bounded by have fact 2, that this is less than or equal to this, by apply abs add. Beautiful. This is less than 1, except it's the other way around. So maybe rewrite. Rewrite. Now I'm gonna make it really, no, I'm not gonna do, yeah, let me do one slick thing. Add sub com at, where do you want to do it? At HN? Whoops, abs. Yeah, it's only slick if you get the name right. So you see the rewrite figured out that I'm looking for a pattern with a subtraction and absolute value, found that pattern and just did it without saying what it was. But I actually don't want you doing that because I would consider that a naked rewrite. Without it's a rewrite without saying what the rewrite is doing. Sean.
I don't think it actually. They're not red. No.
There's red? Oh, they're the same. At H capital N. Let's see. Where's red? Oh, it's that it didn't delete it. This is a bug. This is a bug that it's not deleting things when it looks like it's deleting it. Or am I just not seeing that it's still there? Now it's fixed. Okay, good. So again, we're looking for the AN. The AN is equal to this. This is at most that. This is at most 1. That's AN. So I have the AN, I have the 1, and this sum is non-negative. So we're done. Linearith. Linearith. Come on. Linearith with what? F1, F2, and H capital N. And that's not going to be enough because F1 gets us here, F2 gets us there, H gets us there, and I need the non-negativity of this, which is sum n. Too many M's. Is there another? There's not another. So hopefully if I take that extra M off. That is frustrating. And instead of giving me a nice big, yay, we did it, we had to wait for it. All right. So that's it. Cauchy sequences. Quiz on Tuesday in preparation for the midterm. 2 Tuesdays. Homework due, office hours, Friday morning, recitation. If you want to talk about any of this stuff, Maddie is an expert on these things, so she can help you. We're getting to the point, hopefully we're finally, I've made you 2 promises that lean would not be painful eventually, and that I would tell you what the real numbers are. And we're making, I think, some steady progress towards both of those. I hope you are feeling that. So see you Friday.